All right, let's go ahead and get started. I hope everybody had a great day today. Tonight we're going to be transitioning from DC to AC studies. So we're going to be looking at an introduction to AC electronics. I believe that you're going to find this to be more challenging, but very doable. Okay, let's get started. Okay, one of the things that we do in electrical engineering are a lot of plots. And one of the plots that we find real useful is the same thing that we see on an oscilloscope. An oscilloscope is a device that we use to measure voltages and currents in primarily AC systems, but they could be used in DC systems as well. So I'm going to start by showing what a waveform would look like on an oscilloscope if it were a DC waveform. Okay, but first we got to describe what we're looking at in terms of the plot. This is effectively a Cartesian coordinate system. Okay, in other words, we've got a horizontal axis, we have a vertical axis, which is our x and our y axis. Okay, but our x-axis, our horizontal axis, is going to be labeled with the units of time. Okay, and we're going to have seconds as our base unit. The vertical axis on an oscilloscope displays voltage. So I'll just put E to represent voltage because we're real familiar with that. Now, this right here, representing time, obviously would be our starting point. So this would be time equals 0. Okay? If I were to draw hash marks that were equally spaced along this x-axis or this time axis right here, this would represent like 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. So now we're dealing with something that is changing with respect to time. Okay? And we're going to contrast that to what happens when we superimpose a DC signal onto an oscilloscope. If we were to take a DC signal, and let's just move over here to the right a little bit, and let's draw a simple DC circuit that has one battery or one regulated power supply and one resistor. And let's just say that this was 20 volts. So this is the voltage of the source. And this is the resistance of the load. And let's say this was 100 ohms. Okay. If we were to insert a switch into this circuit right here, the way that it's shown right now, would it be fair to say that the switch is open and that no current would flow? Right. Obviously, no current can flow in the circuit because we don't have a closed loop. Right? In other words, as we go around the loop, we come to this point right here, and then all of a sudden we have it open. So no current can flow. Okay? If at, let's say, time equals 0, we start the stopwatch. Okay? We start the time counting. And at that exact moment, we close the switch. Well, closing the switch is really the same thing as erasing the switch and just drawing in a hard line there. Okay, electrically there's no difference between the two. Okay, with the exception that that if you have a switch in a circuit, you're going to have some contact resistance. If you don't have a switch in a circuit, you're going to have no contact resistance associated with the switch. So there is a little bit of difference. But we're going to assume that our switch is an ideal switch and it has no contact resistance. Okay. So in this circuit right here, which is the DC circuit, we have 20 volts. Okay. What have we learned the voltage would be across this resistor if we put a voltmeter across it? 20 volts. Right. And that's by Kirchhoff's voltage law. The sum of the voltages around any closed loop have to be equal to 0. Or stated in a more simple term, or more simple terms, this voltage has to be the same as this voltage. So this is 20 volts. So if we're plotting the voltage across the load with respect to time, okay, then what we're going to have to do is we're going to have to find 20 volts. So let's just say that this is 0 volts right here, and let's just say that this mark represented 10 volts, and let's say that this mark right here represented 20 volts. Okay? Now, if I'm going to plot, and let me redraw this down here below the circuit so that it'll be easier to see them both at the same time. If I have this circuit right here, which has a 20 volt source and a resistance that has a 100 ohm load, okay, and all I'm plotting on this Cartesian coordinate system, okay, which is also known as the time domain. This is something that I'm going to drill you on because you're going to see this on aptitude exams in industry and also on quizzes and tests in this class. So this plot right here is known as the time domain. And all it is just a fancy way of saying a plot of voltage versus time. Okay? So if I were going to draw a line that was going to represent the voltage versus time on this Cartesian coordinate system, what would the waveform look like? It would look like a flat line. And it would start where?
Right there.
Right here at 20 volts. And it would just go as straight as I can draw the line out to infinity, assuming that we left the thing on forever. Okay? So this represents a DC system. Now you might ask, well, why didn't we look at this when we were studying DC circuits? And the answer is that it provides really very little useful information. Okay? Because all it is just a straight line and it never changes. Okay? Now, if we were to, let's say, hypothetically make a break in the circuit, or if we go back to our switch again, let's say that we were to open our switch. So our switch is in the open position. Okay? And we did that, let's just say hypothetically, we did that at 1, 2, 3, 4, 5, 6 seconds. If we did that at the 6-second mark, what happens to our waveform? It drops. And in an ideal system, it would drop straight down. Okay? And it would drop down to 0. Okay? Because if we're measuring the voltage across the resistor right here, obviously there can be no current flowing through the resistor if there's an open here, can there? And we know that voltage is equal to current multiplied by resistance. And if the current is 0, 0 times anything is what? 0. Okay. So that means that our waveform was at 20 volts continuously and then dropped down to 0 volts and remains at 0 volts until you close the switch again. Okay? So you get the idea how the waveform applies to a DC circuit? Now, what I like to do is I like to make kind of a hokey analogy on how we could take a regulated DC power supply and we could create an AC waveform. And if you understand that, then you have the fundamental understanding of the differences between DC systems and AC systems. Okay? So let's do that. As a matter of fact, let's do that right here. Let's say that we had our regulated DC power supply, and I'm going to draw it like we see it in the lab. We have an analog meter here, which measures voltage. We have an analog meter here. What does that guy measure? Current. That guy measures current, or amps. Okay? And then we have a knob here. And what does that knob do when we turn it? Right, it changes the voltage. Okay, and this is the coarse setting on the voltage, and then the next knob down is the fine setting on the voltage so that we can get it dialed into a real accurate number. And then the third knob down is a knob that we can use to set what the maximum current is that the regulated DC power supply will produce. Okay, but for the purpose of this explanation, we're not going to worry about the current setting. We're just going to say that it's set to generate an amp. Okay. Now, when we come down here to where the binding posts are, or where we actually hook on to the DC power supply, we find that the middle binding post is actually an earth ground. Okay, and so that's used for safety, and it's used in some experiments, not used in other experiments. You don't have to have a ground in a circuit for the circuit to work. Grounds really come out of a need for safety. Okay, so what we're going to do is we're going to focus on our positive terminal and our negative terminal on our DC power supply. And what we're going to do is we're going to hook up the resistor that we have in the circuit to the positive and negative terminal. So basically we have this same circuit, but I'm going to redraw the switch as a closed circuit so that current can flow. Okay? So basically, here's our voltage source. This is where we're getting our voltage from our regulated power supply. And this is our load resistor right here. Okay? So this is the resistor, which is equal to 100 ohms. Okay? Now, you have to bear with me a little bit on this. Okay? Let's assume for a moment that we had a two-man team. And with a two-man team, we were going to use this regulated DC power supply to generate alternating current. This is how we would do it. Okay? One of the team members would be the knob turner. Okay? So one of the team members is going to have their finger on the voltage knob. And they're going to start out with the voltage all the way down at 0. So let me come back to the plot on our oscilloscope, and let me erase the waveform, because we're going to have a new waveform now. If we have a stopwatch, okay, that's basically keeping track of time, and we have one team member with their finger on the knob, and the other team member with their fingers on these two leads right here. Okay? So as we know, these leads right here, you know, can be plugged in. You can either use alligator clips or banana leads or any kind of lead you want. But you have to make contact with these binding posts right here. Okay? So one team member has a hold of these two leads right here. The other team member has a hold of this knob right here. Okay? So we're starting out with the circuit wired up like this, where the left side of the circuit is positive, the right side of the circuit is negative. We have a resistor, so it's going to draw current, okay, if there's voltage. And we're going to start out with a voltage at 0. So if at the moment that we start out with a voltage at 0, we start the stopwatch. Okay? Where are we on this Cartesian coordinate system or on the oscilloscope? In other words, if I had to draw a point to show where we are, we'd be at 0 volts and 0 time, right there. Okay? That would be where we would be. Okay? Now, let's say that we allow 100 milliseconds to go by. Okay? Which is a tenth of a second. That's pretty fast to be reacting as humans, but let's just say we could do it hypothetically. Okay? We'll allow 100 milliseconds to go by, a tenth of a second. And at that time, we then begin turning the knob for the voltage. And as we turn the knob for the voltage, what we do is we turn the knob in a continuous manner such that it creates dots that look like this. And then we get to the point where the knob is turned all the way clockwise. In other words, the voltage is as high as it can go. Okay? So we're up here at 20 volts. So this point right here is at 20 volts. This point was at, something less than 20. This point was lower, 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 and so on. Okay? Now, the person that's turning the knob gets to the full clockwise stop limit on the regulated power supply, and at that instant begins turning the knob back in the opposite direction. What happens to the voltage? Is the voltage going down now? Right. So the voltage is going to start to go down. Okay? So if we continue turning the knob counterclockwise until the knob reaches the point where we can't turn it anymore, we could create a set of points that would take us all the way back to 0 volts. Is everybody with me? So we started out at 0 volts. We turned the knob all the way up to 20 volts. And then as soon as we got to 20 volts, we turned the knob all the way back to 0 volts. Okay? And then what we did is we drew a line that connected all the dots. So there's a line connecting all the dots. Now, at the instant that team member number 2, who remember has his hands on these leads right here, at the instant that that team member sees that this knob has been turned counterclockwise back and has stopped, and we're at 0 volts, that team member takes these leads, pulls them out, and swaps them, and then sticks them back in. Okay? So in other words, the polarity changes from plus minus to minus plus. Okay? Because the leads have been pulled out and swapped over and stuck back in. Okay? Now, when we do that, if we take a look at the circuit itself, what's happened to the direction of the current that's flowing through this resistor, or this resistor here? In other words, when we were on the positive half cycle of this waveform, the current was flowing out of the negative terminal and up through the resistor. Okay? Now, once we take the leads out and swap their polarity, okay, and start preparing ourselves to turn the knob back to a positive voltage again, what's going to happen to the direction of the current flow? It reverses, because what we've done by taking the leads and pulling them out and swapping them is we've taken these polarities and swapped them from positive negative to negative positive. And remember, with electron flow, the current always leaves what terminal of the battery? Or the negative terminal. Okay. So now, and we'll draw this in red. Can we see red okay? Okay. All right. So, and as a matter of fact, what I'm going to do is I'm going to show the way that it was when we started with black. It was at positive, negative, and then we switched it over to negative, positive. Okay? Now the current is going to come out of the negative terminal of the battery, but the negative terminal of the battery is on top. It's not on the bottom. Okay? So if we follow the current flow around the circuit, we see that the current is now flowing in the opposite direction. Okay? So if team member number 1 begins to turn the voltage up by twisting this knob to the right after the leads have been switched, then what's going to happen is, and I'm going to erase the labels here, what's going to happen is we are going to have voltage that's going to be increasing in the same way that it did on the positive half cycle, but it's going to be on what we call the negative half cycle. So in other words, if this point here represented the knob being turned all the way to the right or clockwise to the point where it stops, then this right here would represent how many volts? It would represent negative 20 volts. Okay? Which is the same as 20 positive, except that what's changed? The direction of the current flow. That's what's changed. Okay, so team member number 1 has cranked the voltage up as far as you can go to the right. The knob won't turn anymore, and so he immediately starts cranking the voltage back counterclockwise. As he cranks the voltage back counterclockwise, he creates a bunch of dots that look like this until he gets back to 0 again. So let me extend our time axis here. Until he gets back to 0 again. So if we connect the red dots with a line, this part of the waveform constitutes the negative half cycle of the AC waveform. This is the positive half cycle. Why? Because this is positive voltage. This is the negative half cycle. Why? Because this is negative voltage. Now, it's not negative voltage from the standpoint that it doesn't exist. It's negative voltage only because of what? Direction of current and or polarity. Okay? We pulled the leads out, we swapped them. Okay? And that caused the current to flow in the opposite direction. Now, obviously, we're not going to create AC signals or AC power in the way that I've just described. Okay? But this would be one complete cycle of an AC waveform. Alternating current. In other words, half of the time the current was flowing from the bottom up. The other half of the time the current was flowing from the top down. Okay? So you've got the current flowing in one direction half the time and in the other direction the other half the time. The limitation of doing this is that practically it's a joke. You could never do anything useful with it. Because number one, it'd be very difficult to create a true sinusoid by just controlling the knob. But it's possible. Okay? So this is how you could take a regulated DC supply, and again, this is a DC supply. You can take a DC supply and you can create an AC waveform. This is the basis of AC. The difference between this description that I've just given, where we create it using this almost nonsense technique, and the way that we actually do it, is that the way we actually do it is with generators, rotating electrical machinery. And the machinery is typically rotating at RPMs like 3,600 RPM or, something in that order. All machines, or lots of machines have different rotating speeds. But clearly, if a machine is spinning around at 3600 RPM, it's not going to take that much time to create this waveform. Okay? Even though this was created with a DC supply, it still would be considered an AC waveform. The reason is because it has a positive half cycle and it has a negative half cycle. Okay, so let me stop here for a second, because what I'm going to do is from here we're going to go on and we're going to define some of the important parameters or values that you're going to need to know about AC waveforms. And before we do that, I want to see if there are any questions or comments or observations about what I just described right here. Does everybody see that, you know, we could do this if we wanted to? Okay? And does everybody see that the current is going to change when we yank the wires out and we switch their polarity? Okay? And that's really what's constituting the alternating current, or the change in the direction of the current flow. Okay? No questions or observations? Okay. Good deal. Now, with that as our introductory description of AC waveforms, what I'm going to do is I'm going to write the time domain again. And again, this terminology, time domain, is not used extensively. The reason that I'm emphasizing it is because let's say that you're a foreman for a power company and you're sitting in on a meeting, and the meeting consists of engineers and physicists and chemists and, you know, all different types of professionals. Okay? You might find that somebody who comes from an engineering background will say something like, the time domain analysis showed that we had a fault, you know, at the number 6 breaker. Okay, and what I'm doing is I'm just trying to clarify for you that really all they're doing when they say that is they're just saying, when we hooked an oscilloscope up and we looked at the output of the oscilloscope, we were able to see where the short was. Okay? So what we see when we look at the output of an oscilloscope is the time domain. Again, time versus voltage. And this can be current. This can also be current. But typically it's voltage. Okay? So let's go ahead and let's draw an AC waveform. This is called a sinusoid, or a sinusoidal waveform. Okay? Or for short, sine wave. Okay? Every time that you're on the line and the line is above 0, you're in a positive half cycle. Every time that you're on the line and the line is below 0, you're on a negative half cycle. So we have positive half cycle, negative half cycle. Positive half cycle, negative half cycle. Okay? Now, there's terminology that we have to become familiar with before we start analyzing circuits. Okay? Things like frequency, period, peak voltage, average voltage, RMS voltage, things like this. Okay? And so what I want to do is I want to define those for you and show you why they're labeled as they're labeled. If we come back and scan back to our original explanation of the difference between AC and DC, this would be considered one full cycle. The reason it's considered one full cycle is because when we first started out, we started out at 0 going up. Are you with me? Okay? When we ended right here, if we were to imagine this waveform to continue going on in the same fashion, where would we be? We would be at 0 going up. This constitutes one full cycle. This is a half cycle. This is another half cycle. This is a full cycle. Okay? One full cycle. So if we come over to a waveform that we just see on an oscilloscope, and let's say this waveform is actually being generated from a Honda generator that you buy, at a Honda dealership. And this is, let's say that this is running at 60 cycles per second because you're going to be running, regular equipment, farm equipment off of it. Okay, so let's just say that we're looking at the waveform coming off of a Honda generator that's generating 60 cycles per second. Okay, and 60 cycles per second is the predominant frequency that's used in the United States. Okay, the reason that everybody has to use the same frequency is because most all of the power grids are interconnected. And if you tried to run interconnected power grids at different frequencies, the system would crash. The system would not run smoothly. Okay, so everybody has to decide on a frequency, decide that they can live with it, and then build all of their equipment so that it's going to run at that frequency. In contrast to what we see in the United States, which is a sine wave that is operating at 60 cycles per second, which is also known as hertz. What do we see in the UK or in Europe? We see 50. So they've all decided on a different standard. You notice that they're very close to our standard. They're only 10 cycles per second off. Okay? But if you go to Europe, everything's at 50. In the United States, everything's at 60. And we'll get into some reasons why. Okay? But the U.S. could switch over to 50. It's just that they'd have to change out all the equipment that they've purchased, which would cost billions of dollars. So it's never going to happen. That's why you have to buy a converter, if you're going to take your hair dryer to Paris, right? You can't run off of the same electrical signal coming off the receptacle in the hotel room in Paris if you take a hair dryer that you purchased in the U.S. Exactly. All right. So coming back again to our definition of one cycle, if this is the point at which we started going positive, follow the waveform. It's going positive, it reaches a peak up here, and then it starts going negative, and then it goes through 0. We call this point right here a 0 crossover. Okay, this is called a 0 crossover. The waveform then continues until it reaches a peak negative voltage. And if the signal is symmetric, what's going to be the difference between the peak positive voltage and the peak negative voltage? Right, just the polarity. In other words, the magnitude is going to be the same. If it's 20 volts, 100 volts, 187 volts, whatever it is, if it's 20 here, it's going to be 20 here. If it's 500 here, it's going to be 500 here. Okay? It's just the polarity that's changed. Now, as we follow our waveform again and we come to our next zero crossover, we notice that our waveform is starting to head back to another positive peak. Okay? So this point right here is the point where the waveform is starting to repeat itself. Can you see that? In other words, the waveform started going up, went through its thing, and then it starts going up again. That constitutes what we call one period of the waveform. And the period of a waveform is designated with a capital T. Now, a lot of people think that when they're looking at an oscilloscope, which is a device that allows us to actually see what the voltage signature looks like in an electrical system, they think they're looking at frequency. They are not looking directly at frequency. They are looking directly at period. Why? Because the unit on the horizontal axis is what? No, the unit. The unit is time. Okay, in seconds or milliseconds or microseconds or some metric equivalent of seconds. Now, obviously, we can see the effect of frequency getting bigger or getting smaller when we look in the time domain at the period, okay? But we're not looking directly at the frequency. We're looking directly at how long it takes the waveform to repeat itself. That's what we're seeing. We're seeing other things as well, like we're seeing the peak voltage positive, the peak voltage negative. We're seeing other things as well. But the primary thing that we're seeing is how long does it take the waveform to go through one full cycle. So now comes the relationship between period, which is in cycles. Well, let's figure out what it is. The unit on period, okay? The unit on period would be seconds per cycle. So period, capital T, has the unit of seconds per cycle. In other words, how much time does it take me to go from here to here? And on an oscilloscope, you can measure that very accurately. Okay? Now, with the older oscilloscopes, they don't have cool digital displays that also tell them what the frequency is. On the newer oscilloscopes, they do. So it'll display what we see right here, which is the time domain of the waveform, which shows us basically period and a lot of other things. Okay? But off in the corner, it'll tell us the frequency is equal to something. It'll do a calculation, internal, inside the box itself. You know, it has a microprocessor, and it'll do a calculation and figure out the frequency. The older oscilloscopes don't have that feature. Okay, so it's important that you understand how you can figure out what the frequency is of a waveform if you have an older oscilloscope. Okay, so we're going to look at that formula. It's a very simple formula. they are inversely related to each other. In other words, frequency, which is measured in cycles per second, is simply equal to 1 divided by the period. In other words, if you know how many milliseconds it took the waveform to complete one full cycle, and you take those milliseconds and invert them, then you know the frequency that you're looking at. Okay? So let's do a quick example.
We'll do 60 hertz. That's our frequency.
Okay, let's do 60 hertz and let's work backwards from that. Okay? Because it also the other is true. In other words, if you want to know what period is, it's the inverse. It's equal to the inverse of frequency. Okay, so let's do 60. That sounds good. Okay, so if we're trying to figure out what the period is going to be for a 60 cycle system, then that's going to be 1 divided by 60 cycles per second. So what's 1 divided by 60 on your calculator? This is equal to, what is it? 0.0167 if we round up. Is that right? Okay. And if we look at the units, we have to reverse this for period, right? Because period is equal to seconds per cycle. Okay? So this time right here would be 0.0167 seconds for a signal that you would go and measure at your house in a receptacle in the wall. If you took an oscilloscope out of this lab and you took it home and you measured the voltage waveform that was inside of the receptacle of one of your receptacles in your house, you would find that the amount of time that it takes the waveform to repeat itself in a 60 cycle system is 0.0167 seconds. If we were to convert that to milliseconds, what would that be? 1, 2, 3. That would be 16.7 milliseconds. Okay? So in the United States, it takes 16.7 milliseconds for the cycle to repeat itself. Okay? The other way to look at it is if we're talking about frequency, and we're talking about the frequency in the United States, 60 cycles per second, that means that the current is changing direction how many times in 1 second?
No, 120. No,
Think about that.
the current is changing direction
Think.
For every cycle it goes
twice every cycle.
So in this positive half cycle, the current was flowing in one direction, right?
Yeah.
In this positive half cycle, it changed to another.
So it's 120 times.
Okay, so this changed, it actually only changed once in the cycle.
Oh, it only changed?
It only changed once.
Oh, I see.
So in a 60 cycle system, the current is changing direction 60 times a second. Okay? Now, 60 cycles per second is not high frequency. That's pretty low frequency. But, you know, for the human motor controls and motor skills and motor dexterity, it's pretty fast. In other words, if I said, you know, stomp your foot, you know, on the floor, and I want your rhythm to be 60 cycles per second, right? You're not going to be able to do it. You can't slam your foot against the floor 60 times in 1 second. 1, 1,000, 2, 1,000, 3, 1,000. You can't, I mean, there's no way. You can't do it. Okay. All right. So, very, very, very important to understand the difference between the period of an AC waveform and the frequency of an AC waveform. They're related to each other by a simple inverse. If you know one, you can find the other. All you have to do is invert it. Okay? And let's take a look very briefly at the units if we move over here. Okay? We said that period is equal to the inverse of frequency, and we said that we're going to use a 60 cycle system because we know that's what we have in the United States. So we wanted to find what the period was in a 60 cycle system. So he said period T is equal to 1 over F, the inverse of frequency, okay, which is 1 over 60. Okay? Our calculators told us that it was 0.0167, okay, but when we have cycles per second in the denominator, what are the units going to come out as when they move up into the numerator? Seconds per cycle. Which is equal to hertz. And that's the primary unit of measure for frequency, is hertz, abbreviated Hz. Okay? Any questions on this? How many of you have ever seen this before? Okay? How many of you kind of get it? Okay. So if you looked at this again, I mean, obviously we're taping this. If you look at this again, look at it a couple of times, not a big deal, right? I mean, this really isn't rocket science. Okay? Okay. Now, let's switch modes and talk about some other characteristics of the sine wave that we're going to need to know in order to work in the industry. We just found out that the amount of time that the waveform takes to repeat itself, in other words, go through one full cycle, that's represented by the capital letter T, which is called the period of the waveform. Okay? Another very important characteristic that you're going to have to be familiar with is what we call peak voltage. Peak voltage or peak current. And that's pretty straightforward. That's as big as it gets. The peak voltage is the point that defines the highest value that the waveform gets to. Okay? In a symmetric.
Is it the same for the negative too?
Good question. If you have symmetry in a balanced system, yes. Absolutely. Okay? So, if this guy is, let's talk about what we have at home. At home, how many volts do you have coming out of your receptacle? 120. 120 volts. What is that value, 120? Does that represent the peak value or something else?
RMS.
It represents what we call the root mean square value of the voltage, which is a fancy way of averaging. So the voltage coming out of our home is equal to 120 volts RMS. And RMS is root mean square. Okay? So the 120 volts is root mean square. Now, it turns out that the peak value is not the RMS value. The RMS value is down here somewhere. The RMS value is also known as the DC equivalent. So it's the value that would be equivalent in a DC system. So this is 120 volts. The peak voltage is related to the RMS voltage by a factor of square root of 2. Okay? So if you want to know what the peak voltage is, the peak voltage is equal to the square root of 2 times the voltage RMS. Anybody have a calculator?
It's always like that.
Yes, I have.
Anybody have a calculator? What's the square root of 2 times 120?
480. No.
What's the square root of 2 times 120?
Oh, wait a second.
No, just put it in your calculator.
Sorry. 169.7.
169. So this is negative 169 volts. And guess what? That's the negative peak voltage. This is the positive peak voltage. So if you go home and you measure the voltage coming out of your receptacle, you're not going to find 120 volts. You're going to find 169 volts. Is that what you got? 169? Okay? All right. Now, there are several other values that are associated with this waveform, like average voltage, duty cycle, modulation, et cetera, which we'll get into in our next lecture. Okay? But for now, this is enough to get started. The value that we are used to associating with the voltage that comes out of the receptacle in our home is actually a DC equivalent voltage, which is a fancy way of averaging this sine wave. That's the 120. And it doesn't change. It stays constant. That's why I drew a straight line. But when you actually go to your house and you check the voltage in the receptacle, you're going to find out that it's not constant. It's going like the ocean, right? It's a wave. It's a symmetric sinusoidal wave. Okay? And so we learned that the period is the time it takes the waveform to repeat itself. The frequency is the inverse of the period and measured in cycles per second or hertz. The highest value is the positive peak voltage. The lowest value is the negative peak voltage. And for people living in the United States, that value is around 170 volts. Okay? So you can see huge difference between DC and AC. DC is constant and never changes. AC is constantly changing. Back and forth, back and forth, back and forth, back and forth. Any questions? No? Okay. All right. Well, we've run out of time this evening, but we will pick up where we left off here next time. Drive safely. Have a good night.